So from the scientific method, the results that we end up articulating are useful in displaying certain bits of information that will later allow us to reduce our intersection with natural processes, and hence prevent those processes from becoming hazards, right? As we are no longer intersecting or being involved with the processes. Or we can, through this, look into the future and say, this is what is necessary to reduce the hazard risk for future events. So the scientific method allows us to look at simple information such as what locations are more likely to receive a specific natural hazard and estimate the likelihood of them occurring in that location, just based again on the geography and on the settings, geographical settings. So we can also estimate, for example, the probability of occurrence for natural hazards in the futures. And a good way to do this is by historical accounts of the same event occurring before over and over. So the periodicity or the time interval between natural hazards is a good starting point to estimate when the next natural hazard could occur. So again, historical based. So an example that I have is here in the Boise area, especially near the river, right, in the floodplain. So we know that we should expect the flooding event of a certain height above the normal river stage. The stage is pretty much the level at which the river sits. So we expect a flooding event of a certain stage level, a certain height, above the normal stage every 10 years. But we also know that we also should expect a greater flooding event of larger height above the normal river stage that could happen every 100 years. So these expectations that we have of flooding events occurring or to occur are called recurring intervals, okay? And we'll refer to them again as the course goes by. One of our labs in the flooding chapter is pretty much based solely on recurring, or not solely, but a large amount is based on recurring intervals. So it will deal with them. Let's see. So the scientific method also allows us to determine whether a natural event may happen based on precursor events. So precursor events are events that typically occur prior to the natural hazard. For example, in the slide, if indeed our hypothesis of the slope being oversaturated was the cause for the landslide, then the precursor event would be a large amount of rainfall in an already saturated slope, right? That's what we said had happened for this also landslide. So this allows us to make forecasts as to how likely is it for something to occur based on those precursor events that we see happening. This is how, for example, weather forecasters do their job. That is how they are made, partly. Precursor events are especially useful when dealing with volcanic eruptions, for example. So things like seismic activity, like soil expansion or subsidence, or changes in the amount of gases that are being expelled at the crater, are very good telling precursor events that an eruption may happen very soon. So those would be precursor events to the natural process or the natural hazard, depending on what you're dealing with. So again, depending on the precursor event amount and certainty, this allows a quantitative estimate of the likelihood for a natural hazard. Okay, so that's what we're looking at right here. For example, when we have observations of weather patterns, these hint towards a rain event. Again, that's just an example. And they could be somewhat certain, or they could be completely certain based on the setting, on the precursor events, and based on other atmospheric conditions. And hence, based on the certainty, they can give us a percentage of likelihood that it actually does rain, and a duration of that rain event per se. So if we have gathered really good data from previous events, and there is a very clear and exact pattern of recurrence of natural hazards, we may be able to predict to a specific time and date and how large the event will actually be. And again, this is done through observation, through experimentation, and through tracking. So all of that data that we have previously is done through observation, experimentation, and tracking. And if we become really good at getting the exact pattern and the exact date and time, we can actually predict it rather than just forecast it. But that's incredibly hard. For example, hurricanes are natural hazards that we usually do quite a good job at short-term predictions for. So we are decent at predicting how strong they're going to be within a short period of time beforehand, and where they're going to hit based on their speed and energy. So once we have this information or a close enough prediction, warnings can actually be sent out to citizens, to governmental agencies, or to other public or private parties in order for them to act appropriately in a given natural hazard likelihood and in magnitude of damage. So they can probably avoid a natural disaster or catastrophe if being given enough notice and enough warning. So based on all of those things that I had just said, based on all of these bullet points, the scientific method, it does aid us. And by using the information for a location, past events, precursor events, forecasting or prediction, and issuing of warnings, if we look at the also landslide right here, which is again in Washington State, and it was the opening slide for this lecture, we can say that with a large amount of snowmelt and rainfall experienced in an already humid area, it was the rainfall that was responsible for such a landslide. And that in the future, if similar conditions are experienced, meaning heavy snowmelt and a heavy spring precipitation, then communities near the area should be warned of a potential landslide event again and take measures of either strengthening their properties or perhaps of full evacuation to at least save their lives. All right, so all of that I had just said in the previous slide is pretty much summarized into what we call a risk assessment. So when we think about our observations and some natural hazard that we're trying to prevent, we're going to think about our observations as data, okay? So after we have our observations and we made our conclusion and whatnot based on the process, we're going to process that information as scientists. Then we're going to go ahead and pass that information and analysis to a prediction review group. And you may be part of that prediction review group as being a scientist yourself. Once you have a prediction review group that makes a prediction of natural hazard occurrence or recurrence, the results are then given to a regional official to the public. So you're going to give it either to the regional officials or you're going to give it straight to the public, depending on the regulations of your area and perhaps depending on the necessity of this natural hazard to be talked about. So the regional officials themselves will in turn choose to either give that prediction to the public themselves or to just local officials. The regional officials may choose not to give a said prediction to the public at all based on their understanding of the situation or perhaps based on financial reasons or other plans that they have in mind that the prediction review group is perhaps unaware of. So usually the course of action is that the prediction review group will give this information to the regional officials, not necessarily to the public right away. Okay? But again, for the most part, once the scientists and the prediction review group assess the data appropriately and hand it off to officials, they tend to provide a summary of that information to the public and warn them, and in some cases they will actually encourage the evacuation of the area where a particular natural process or natural event is going to happen. All right, so now we're going to go ahead and jump in and talk about what risk is. So what is risk? Risk is going to be a function that is measured as the probability of something occurring times the consequences that would come if that something occurred. Okay, so again, it's a function of the probability of something occurring times the consequences of that event from occurring. So if you have an event that is likely to happen, meaning it has a high probability or a great probability, but the consequences of it happening are relatively low, then your risk falls in the middle category. So again, probability relatively high, but consequences are relatively low, so you match those up, and the risk overall would fall in this middle area, this kind of yellow part. So an example for that former case, again, where the probability is relatively high, but the consequences are relatively low, is that you get a cold this year. Sometime this year, you either got a cold or will get a cold. So the probability of that happening are pretty high. As you probably have seen, most people get sick at least once, oftentimes more than once a year. But the consequences of that cold killing you or causing major damage to your system are quite low. Again, this is if you have the common cold, not the flu or some other type of coronavirus or anything along those lines. So just the common cold, and that you have no underlying conditions. So that would be a good example for having high probability, low consequences. So your risk is kind of in the middle. An example for a second case where you have high consequences and lower probability would be that a plane that you're in crashes. So the probability of a plane crash from occurring is relatively low. This doesn't happen often, but the consequences would be very likely death for the most part. So the consequences would be very high. So death would happen, if not to everybody in the plane, to most of them. So your risk falls in the same category as getting a cold. Again, this is just based on probability and consequences, because that is what risk is. It's a function of those two things playing along. So let's go through a few different examples that I have for you here in the slide. So if we consider a hailstorm in Nampa, the probability of it occurring is quite high, right? And the consequences tend to be mostly low, unless it's one of those kind of hellish hailstorms with hailstones the size of golf balls or even larger. So if it's a normal hailstorm, we could say sure, probability is about 4. The consequences is 1 to 2, so the risk is kind of in the lower middle area, right? If we consider, for example, an earthquake occurring in Nampa as the epicenter, based on tectonic location and regime, the probability is relatively low, and we'll hopefully get to that in the next few chapters. So probability of an earthquake occurring in Nampa, meaning the epicenter being in Nampa, is relatively low. So I'm going to put it around a 2. But the consequences could be higher than if the earthquake had happened in Stanley, for example, right? Because the population is much larger in Nampa than it is in Stanley. So if you remember, in the spring of 2020, there was an earthquake near Stanley, between Stanley and Chalice area. And thankfully, we saw very little consequences associated with that, partly because of the low population in that area of Idaho. Let's see. So the next one is earthquake in LA. So if we consider an earthquake occurring in LA, based on the tectonic location and on the regime where they're at, the probability of it occurring is actually quite high, between a 4 and a 5 probably. And this is based on the San Andreas Fault crossing through the city, basically, or near enough that it would cause major damage. And if it is due, meaning if it's bound to happen, which in the next few years is bound to do so, we know that the consequences could be very high, since LA has a lot of people, and that these people are spread out throughout a lot of land with buildings and roads that would be all would all have to be repaired if they got damaged. So the risk in this scenario, being a high probability and a pretty high consequence, would be high. So the risk in this case, an earthquake in LA, would be very high.